So, imagine you're writing a single line of code, right?
Okay.
And this code makes your program just mathematically perfect.
Oh, like infinitely scalable.
Exactly. Infinitely scalable. But, and here's the kicker, it is incredibly likely to just break your entire system next week.
Yeah, a total landmine.
Right. You look at the flaw, you acknowledge the landmine you've just planted, and then you just decide to keep it anyway.
Which is wild.
It is. And today we are looking at a developer who did exactly that. Welcome to the deep dive. Our mission today is to step directly into the mind of a programmer by examining a highly specific, really densely packed journal entry they wrote.
Yeah, we're basically looking over the shoulder of a software developer today.
We are. And we want to unpack the philosophy behind what seems like a trivial technical decision.
Right, so the developer's name is Ang, and the source we're looking at is an excerpt from a blog post titled Haskell Optimization, Constant Time Metadata Extraction. It's actually part 145 of their Notes on Haskell Programming, published on May 26, 2026.
Part 145. That is a lot of notes.
Oh, it's a huge series, yeah. But what makes this specific entry so compelling is that it captures this universal architectural dilemma in real time, like as they are coding it.
Right, right. And the setup here is something you've likely encountered if you've ever worked on any kind of document processing. So Ang is working on a pet project, mapping custom parser output to a pandas abstract syntax tree.
An AST.
Exactly, an AST. And the immediate roadblock is a classic one. They're just trying to extract keywords from the document's metadata.
Too simple enough.
You'd think. So, okay, let's unpack this. Because we are about to go on a journey that starts with a very declarative, safe approach to extracting data, and it ends up in a surprisingly deep debate about, system fragility and the very nature of optimization.
Yeah, to understand the optimization Ang actually attempts, we have to start by looking at the architecture of the first approach, the original code.
Right.
When you're mapping a custom format to a pandas AST, you are essentially translating your document into a universal tree of nodes.
Like headers, paragraphs, that kind of stuff.
Exactly. Headers, block quotes, and of course, metadata blocks. Your parser spits out this token stream representing all these elements. And Ang's initial goal was just to traverse that token stream and pull out the keywords.
And the original code snippet Ang provides to do this uses a list comprehension. For those following along, it's written as keywords equals K, where tmeta_md is drawn from tokens, and then K is drawn from the index of MD.
Yeah, and for anyone writing Haskell, this is incredibly idiomatic.
It's super standard.
You're taking your list of tokens, filtering it to find the tmeta, which are the metadata tokens, and then extracting the keywords from the index of that metadata.
It's a purely declarative statement, right? Like, the code doesn't care about the structure of your document.
Not at all.
It just says, hey, search this entire stream of tokens, and wherever you see a metadata block, just give me the keywords.
Right. Because it's a list comprehension, it operates on the entire spine of the list. It looks at the first token, checks if it's tmeta, then it moves to the second, then the third, checking literally every single node in the AST until the list is completely exhausted.
And translating this into the performance characteristics mentioned in the post, this is an ON operation.
Yes.
Big O notation.
Right. The time it takes scales linearly with the number of tokens. So to use an analogy, if you're looking for the publisher's information in a printed book, you know it's almost always on the copyright page at the very beginning.
Sure.
This ON list comprehension is like grabbing the book, finding the copyright page, getting the info, and then stubbornly flipping through all 500 remaining pages of the novel.
Just checking every single page.
Literally every page.
Yeah.
Checking chapter headings, the index, the glossary, just in case the publisher hid a second copyright page at the back of the book.
Right.
It is completely exhaustive.
Exhaustive, yeah, but from a purely algorithmic standpoint, mathematically necessary.
Really?
Well, yeah. The list comprehension function doesn't possess any domain knowledge about your specific book or your specific document structure.
It only knows it was instructed to filter a list. So it filters the entire list to guarantee accuracy.
But wait, let's look at the reality of the execution environment here. We are talking about mapping an AST. A modern processor, or even just relying on Haskell's lazy evaluation, can traverse a list of a few thousand tokens in an absolute fraction of a millisecond.
Oh, easily.
Right. So if the parser is already reading the whole document to build the AST in the first place, does an ON search for a metadata token actually register as a real performance hit?
Probably not.
Like, is this a genuine bottleneck for Ang's application, or is this just standard developer neurosis kicking in late at night?
It almost certainly falls into the latter category. It's totally neurosis. But, and if we connect this to the bigger picture, it's a neurosis born from a valid architectural instinct.
Oh, so?
Well, in software design, doing unnecessary work, even if that work takes a microsecond, it creates this conceptual friction.
Conceptual friction. I like that.
Yeah, the developer knows the exhaustive search is happening.
Yeah, yeah.
That knowledge sits in their mind like a splinter. When you look at an ON traversal for something you know shouldn't require it, your instinct is to just align the algorithm with the reality of the data.
Which naturally leads to the realization Ang has in the journal entry. Because Ang isn't just dealing with an arbitrary stream of pandoc tokens.
Right.
They are dealing with tokens generated by their own custom parser.
Exactly.
And that parser operates under a very strict set of domain rules regarding where the metadata lives.
Yes, and this structural realization is the pivot point of the entire post. Ang notes that according to the project's own parsing rules, the metadata is always located at the very top of the file.
Always.
Always. There won't be inline metadata halfway down the page. There won't be a secondary metadata block appended at the end.
Right.
The parser is explicitly designed so there will only ever be a single t-meta token, and it will undeniably be the head of the token list.
Okay, so armed with that domain knowledge, the exhaustive search suddenly looks kind of absurd.
Totally absurd.
So Ang completely abandons the list comprehension and rewrites the extraction logic to use a direct pattern match. The new code simply uses case tokens of. They destructure the list, looking specifically at the head.
Right, the very first item.
Yeah. If the first element is t-meta, extract the keywords and ignore the tail completely.
It is structurally elegant. By pattern matching against the head of the list, the program no longer traverses the spine. It simply inspects the first node in memory.
Wow.
If it matches, you have your data. If it doesn't, it moves on. This changes the fundamental scaling curve of the function entirely.
Because it doesn't matter how long the document is anymore.
Exactly.
Yeah.
It no longer matters that the document is a one-page memo or a 10,000-page technical manual. Checking the first token always takes the exact same amount of compute time.
But here's where it gets really interesting. Because it becomes an O1 operation. Constant time.
Yeah, so
The absolute holy grail of algorithmic efficiency. Your graph of execution time is just a perfectly flat horizontal line regardless of input size. It's beautiful.
it is. Building on our book analogy from earlier, instead of exhaustively flipping through all 500 pages, you are now literally just glancing at the inside cover.
Boom.
Instant result.
You extract the data and you are done.
And I have to say, it is deeply satisfying to write code like that.
Oh, I bet.
You are leveraging the structure of your data to shortcut the compute. It feels sharp. It feels like you've somehow outsmarted the default constraints of the language, you know.
I get that. But I have to bring up the massive caveat hidden right in the middle of this victory lap.
Uh-oh.
Yeah. Ang explicitly admits in the post that since there is only one t-meta token anyway, and it's always the first element, this theoretically brilliant O1 refactor does not really improve the performance.
Yeah. It is a jarring admission of reality to find in a post literally titled Haskell Optimization.
Right. Like, why even write the journal entry? If you are a developer looking at a refactor that you know doesn't yield any tangible millisecond improvement in your actual runtime, why celebrate the constant time extraction? Because the original ON code would have found the token immediately on the first try anyway. And traversing the rest of the list takes practically zero time in a normal document.
True. But the motivation here isn't about benchmarking. It's about theoretical constraint.
Okay, explain that.
So, in the sterile vacuum of computer science theory, upgrading an algorithm from linear time to constant time is an objective triumph.
Okay.
You have mathematically eliminated the possibility of inefficiency. The old list comprehension code could search the whole list, right? Leaving the door open for wasted compute.
Right, right.
But the new pattern matching code cannot. It is structurally constrained to be fast. For a developer, closing that loop and achieving theoretical purity is intoxicating, even if the real-world difference is, frankly, negligible.
But in pursuing that theoretical purity, Ang introduces a completely new and arguably much more dangerous kind of problem into the codebase.
Yeah, they do.
And this is where the journal entry transitions from a clever technical trick into just a masterclass on system fragility, because this constant time optimization has a hidden cost. And it comes down to architectural coupling.
Coupling is the perfect word for it. By writing this O1 pattern match, Ang has taken a localized piece of extraction logic and tightly coupled it to the global behavior of the parser.
Yes.
The elegant solution relies entirely, 100%, on the current parsing rule remaining static forever.
It relies entirely on the assumption that the p-meta token will always be bundled at the very top of the file as a single token.
Exactly.
But anyone who has ever maintained a code base knows that domain rules change. Projects evolve. You get new requirements.
And Ang is actually highly self-aware about this trap. They spell out the exact scenario where the system shatters.
They do.
They note that if, in the future, the architecture changes, for example, if they decide it makes more sense for the parser to emit each individual metadata field as its own separate t-meta token instead of one massive bundle at the top,
Then what happens?
this new O1 approach instantly breaks.
Because the pattern match only destructures the head of the list.
Yeah.
So if the new parser rules put 3 separate metadata tokens at the top of the file, say one for the title, one for the author, one for the date, the case statement grabs the very first one, extracts the title, thinks its job is done, and completely ignores the author and the date tokens sitting right beneath it.
And notice the nature of that failure.
Yeah.
It doesn't throw compilation error.
Oh, wow.
It doesn't crash the program. It just silently drops your data.
That is terrifying.
Silent failures are the absolute worst kind of bugs to track down in a document processing pipeline, because the output still generates. It's just missing pieces.
You wouldn't even know it's broken until someone complains that the author's name is missing.
Exactly.
Contrast that with the original code. The theoretically slow ON list comprehension would have flawlessly handled that parser change.
It would have.
It would have scanned the whole list, found all 3 newly separated t-meta tokens, and extracted every keyword perfectly. The list comprehension was inefficient, but it was incredibly resilient because it was decoupled from the structural order of the file.
Right.
The new code is blazingly fast, but it is utterly brittle.
You are trading a robust, generalized solution for a fragile, highly specific one, all for a performance gain that you've already acknowledged doesn't practically exist.
Right. So what does this all mean? Because Ang's final conclusion is so mind-boggling to me. After realizing the tight coupling, after admitting it doesn't improve real-world performance, and clearly documenting that it creates a brittle system vulnerable to future parser changes, Ang writes, and I'm paraphrasing here, "For now, let's keep it this way, and we can revert to original implementation if we ever change the parsing rule."
Yeah.
I have to push back hard on this logic. Like, as an engineer, isn't this a terrible trade-off?
Oh, from a purely pragmatic standpoint, it is a textbook definition of technical debt.
Right. You are actively choosing to leave a landmine in your Pandoc AST mapping. You are literally documenting the exact way your future self is going to get a headache when the metadata drops out of your documents next year.
Yeah.
Why not just hit undo? The second you realize the flaw, why not revert back to the resilient ON code right then and there?
Well, what's fascinating here is that you are fighting against human psychology, not just computer science. This Part 145 entry offers a really raw, unfiltered look at the realities of maintaining a pet project.
Yeah.
This isn't enterprise software with a strict code review board pushing back on brittle changes.
Right. There's no manager saying, don't do this.
Exactly. This is a single developer tinkering in their own ecosystem. Ang spent the cognitive effort to recognize the domain constraint and design the O1 optimization. To delete it immediately is to admit defeat. It feels like surrendering to inefficiency.
It's like realizing your architecture is flawed, but deciding the code is just too pretty to delete.
Exactly that. By adding the note, we can revert to the original implementation if we ever change the parsing rule. Ang is essentially negotiating with their future self.
I'll fix it later.
Yeah. They're saying, I know this is structurally fragile, but I want to enjoy the satisfaction of having perfectly efficient, constant time extraction for just a little while.
Wow.
It is the intentional creation of technical debt, rationalized and documented in real time.
It's the constant battle between rigid perfection and messy resilience. The O approach was safe, but to a developer's eye, it felt sloppy. The O1 approach is dangerous, but it feels sharp. Given the choice in a TEP project, Ang chose sharp.
It really highlights a broader truth about software engineering. We often talk about code as if it exists in the vacuum of pure logic. But engineering is deeply influenced by the engineer's relationship with the machine. The desire for algorithmic elegance frequently overrides the need for practical durability. You see this in code bases everywhere. Developers over-optimizing for the exact state of the world today, perfectly tuning their logic to current constraints and completely ignoring how that tight coupling will punish them when the world inevitably changes tomorrow.
Let's pull all of this together because what started as a highly specific look at mapping tokens in a Haskell project has actually uncovered a pretty profound narrative about how we design systems.
Absolutely.
To recap this whole journey, Ang started with a foolproof, structurally decoupled ON list comprehension. It was exhaustive and highly resilient to changes in the data shape.
Yeah.
Then, driven by that innate developer itch for efficiency, they leveraged strict domain rules to optimize it down to a lightning-fast O1 pattern match on the head of the list. But in doing so, they realized they had traded global resilience for local speed, a speed they openly admitted was purely theoretical. And ultimately, they accepted that fragile architecture. They intentionally left a brittle system in place just to preserve the elegance of the algorithm.
It is the complete life cycle of a micro-optimization, including the stark realization of its own futility, all contained within a single journal entry.
It's incredible.
And this dynamic connects directly to anyone who builds or organizes complex systems, whether that's in software, business, or just daily life.
Yeah, if you've ever built a complex workflow or designed an architecture for your team, you have faced this exact crossroad.
You really have to ask yourself, when you optimize a process, are you making it flawlessly efficient for today's rigid circumstances? And by doing so, are you simultaneously stripping away its ability to handle the inevitable, messy realities of tomorrow?
Because things will get messy.
Always. It is incredibly easy to build a perfectly tuned routine that shatters the second an unexpected variable is introduced. Resilience usually requires a little bit of slack, a little bit of inefficiency.
But we crave that clean binary logic, even if we have to break our own systems down the line just to pretend we achieved it today. Which leaves us with a final thought for you to mull over, something that lingers long after you close the code editor. If an expert developer, someone who deeply understands the mathematics, the syntax trees, and the architecture, knows that a shortcut doesn't yield practical results and explicitly acknowledges that it makes their system dangerously fragile, why does the psychological allure of theoretical perfection still win out? What does that say about human nature's obsession with the idea of efficiency, even when it actively works against our own long-term survival?